So we've had quite a bit of discussion already, and this is kind of what we're thinking of experimenting. So this would be experiment 1. This would be experiment 2. And this is polar. And this is, I don't know, I guess.
The algorithms.
Yeah. Our homegrown algorithm. So in both cases we have our xy coordinates, but they're sorted differently. So in this case we'd sort by theta to test the polar coordinates with theta and including rho as another feature. In the second experiment, we'd sort these by either x or y and plug it into the greedy algorithm, which just goes along the distance matrix and picks the minimum and then goes to that node and picks the minimum from there. So it's not quite the same as Dijkstra's, which tracks the minimum distance from one point to any, like it creates a minimum path. So it doesn't just take minimum from this point. It will actually give you a path that's the shortest path from any of the given nodes. So these two should look kind of similar, but this one should be closer to optimal. So we'd have our first 40 features are the XY pairs. In this case, we have 40 because we're running 20 coordinates. And then we have our sequence using the greedy algorithm. And then we can also try the sequence from Dijkstra's. So I'm fine to work on giving you a set of features, and then do you mind doing the machine learning and trying out the different things?
Yeah.
So
do you think maybe, I don't know, would sorting by row do anything? Instead of just flip the row and the theta?
Sure, we can try that too. Let's make that a third experiment.
I remember hearing from the other guys that row did have an impact on their sequences. I don't know if sorting by it is going to help or just having it as a feature would, but
I'm also realizing that we need to, well, hold on a second. So this is just sorted by theta, and then I guess, so these are already correlated. In this case, this would be the input we put into these algorithms. I'm just kind of realizing. So we don't necessarily, I mean, we could have these, but we might also want one more set of features. Let's see, this would go to 120, which are the coordinates that it actually outputs as the sequence, if that makes sense.
okay, yeah, the XY coordinates for the sequence points.
Yeah.
Well, so do we need two sets of those, one for the greedy and one for the Dijkstra's?
Yes. That's a good point. So we have 8 million features. Hang on.
That should be 160, right? Because there's
40.
40.
Yes, 160. 160 coordinates of sequence for the greedy algorithm. And this would be for Dijkstra's. Okay, so then this would be sorted by row, which is
That's P. I was just
Yeah.
drew a P in physics.
Yeah, that's much prettier than the word. Let's see. And then, so we'd have, I guess we could make these the row then.
Although that doesn't really matter because those will end up being weighted differently. It doesn't matter what we write them down, right?
Yeah. So I'll just keep it the same, and then so thetas.
And those are sorted by row.
Yeah. And then just the sorted rows. Cool. So we have 3 experiments.
And so I can't think of it, literally any other features that could come out of just the coordinates or the sequences, because we have both coordinate systems, and then we have 2 different ways to figure out a sequence to give it, Um,
Do you want to maybe split up these two, like try just this, and then separately like the Dijkstra's and the Greedy separately, so we don't have a ton of features for one?
yeah, that makes sense. And then we could also do rows and thetas for those, maybe. I mean, like you said, we don't want like too many features, I guess. But like the rows and thetas of the coordinates that they give us. Like similar to experiment 1, except there's just an extra step of those sequences.
Okay. Let's see here. Let's see. 60 sequence of the Greedy, and then 61 through 100 coordinates of sequence.
And then even to save room, you could just do like a theta row pair if you just want to do that instead of having them separately.
What do you mean?
Like when you have the coordinates in polar, it's like it goes theta row, like x, y, instead of having them separate. I mean, I don't know. I thought just like to save room.
I think it would take the same amount of room.
I just mean like writing it up here.
Oh yeah, okay.
No, yeah, I know that they would be like, but like they're paired like x, y would be
Yeah.
for each point.
Okay, I see what you mean. Yeah. So, do you think having the polar in there, even with, because the greedy algorithm and Dijkstra's are based on the Cartesian coordinates rather than polar, so do you think
So it probably wouldn't help necessarily.
that's what I'm wondering, because it might. I mean, it might still help, but I just wonder if that's, like, if it's going to correlate, you know what I mean?
Yeah, probably. Maybe not, just because, like you said, it is based on the Cartesian coordinates. So it would just be kind of out of order and not really provide anything, I would think.
Yeah, that's what I'm thinking. It probably, because they're different coordinate systems, the way that they relate to each other are going to be different. But like sorting by theta versus sorting by rho, like within the polar coordinate system, I think is an interesting, or sorting by rho rather than by theta, I think that's an interesting experiment for sure. Let's see, can it?
That's just making sure.
Yeah, can it? Let's see it. There we go. So what do we say this was? So coordinates. So with this one, I mean, I was testing it sorted by x. Do you want to sort by x or sort by y, or do you think it matters?
It probably honestly doesn't matter.
I'll just continue to sort by x then, just so I don't have to change the code.
Yeah. I don't see why it would matter.
I guess it would only matter if there was, I don't know, I don't know that it would matter, honestly. I think it only matters that it's sorted by something. Is it still showing up?
Yeah, there's a light right in the way, so I'll...
There we go. Cool. This will be interesting for sure.
I think it'll show us what does have an impact and what doesn't. I mean, that's what we're looking for, right?
So, I guess there's well, no, because what we were doing, or at least what I was just trying to do, was I was taking like, well, I was using greedy, but like taking this sequence, that feature, and throwing it to the genetic algorithm, and it did show an improvement, either through results or through time or both. But what we want to do is, like with these all will give us some sort of sequence, hopefully. And then we want to toss this to,
TSP.
yeah, and time it and see. So for every one of these, we want to throw at least one sequence to the genetic algorithm or something like that, because, well, let's see. Oh, no, wait, that's right. We're supposed to have like, it's supposed to be like 20 cities and then like 1 record, 2 records, 3 records, up through like 10 or something like that.
Mm-hmm.
That's a ton of data.
Gonna take a hot second to run.
Yeah. So maybe we can just batch it, like test 2 or test 5 or something,
Mm-hmm.
and see how this works. Or even like, yeah, like if we take 2 and, because we also want to capture the original random coordinates.
Mm-hmm.
So we'll compare, like, say, this sequence as, actually, we won't put a sequence. It'll output a sequence, and then we have to translate that back into XY coordinates, and then throw it to genetic algorithm. So that's the hope anyway, is that this gives us a sequence. And then we turn that sequence back into XY coordinates and throw it to the genetic algorithm and see if it does better than with the random. I'm just thinking out loud. So yeah, we'll have a bunch of like from the sequence. So like 1, 3, 2, whatever. And then, yeah, so we'll then just kind of, so basically instead of taking this point, turning it back into XYs and throwing it here, we'll just run a few more steps and do the same thing.
Uh-huh.
So I think that's about where we're at. Anything more you want to try?
I mean, just like I said, it was the rows. I said that helped, so that was, I mean, like I said, I can't really think of any other features that we can come up with, unless there's another, like, algorithm we can try, but, I mean, there's probably not really a point if we have four experiments already. One of these are bound to give us a better, if they have any impact on it at all, one of them are bound to give us a better result.
Yeah. Yeah. It'll be interesting to see what works better, if anything at all. So what I will do is I will give you, I'll run through the code and give you this feature set, and then you will do this processing part and the test, like validation
Okay.
part. All right. Cool. In this part of the video, I'll be going over our feature set. We use polar coordinates as well as some other features that we've added to see whether it will improve our accuracy with machine learning in MATLAB. I'll go over to MATLAB in just a moment to show you the code. For the instructions, I'll mostly be detailing this third part, showing the X feature matrix and Y target matrix in MATLAB. Keith will then use those features to test MATLAB's machine learning algorithms to see whether we can actually improve the accuracy and get a good warm start. I have the codes in MATLAB, and as you can see, I've already started running it, and it's still running because I'm trying to develop 100 different records for the feature set. But let me explain what each of these does. This machine learning TSP polar pre-processing is what actually produces our feature set, but it relies on these other functions, not including Dijkstra's. I'll explain that in a moment. You can see here that we start off with some random XY coordinates. In this case, we want 10 cities for a given record. Here is where I'm adding in the new feature set. We're not using Dijkstra's algorithm because it was difficult to get something meaningful from it, and I can explain that in just a moment, but I want to focus for now on the greedy algorithm. It takes the XY matrix as an input and outputs a sequence
the resulting distance and the coordinates. Here's that function. This is similar to what I showed in the previous homework video. We're sorting by x, creating a distance matrix, and using big M to set those nodes with the zero distance to big M. And that basically penalizes the zeros in the matrix from a node to itself to avoid using that in the minimum edge calculations. We create a sequence matrix, and then using this block of code right here, we essentially create a route, tracking where we've been and adding to the sequence the next node that has the minimum distance from the previously indexed node. We also, in calculating the total distance, wrap it back around, although that's not accounted for in the sequence, just like it's not in the TSP-GA, where it simply lists each node once. We put those coordinates from this sequence here back into an XY, and then it returns the sequence, the resulting total distance, and the XY coordinates of this sequence here. So as we go down, you can see my attempts at trying to make something meaningful out of Dijkstra's algorithm. Let me explain now why I didn't use this. Dijkstra's algorithm is generally known for producing the shortest distance and path between points. However, as the code itself explains, the code comments do, what happens is if you include a starting ID and a finish ID, it calculates the shortest distance and path between start and finish nodes. So what it does is you have a nodes matrix, which has the ID of each of the coordinate pairs, and a segments, which shows you which nodes may be traced to which other nodes. Well, since in our TSP problem, we don't have a limited number of paths, any node could be the start or the finish and go from there to any other node. What happens when you put in the start ID and the finish ID is it will simply go straight from one to the other. Why would it incorporate other nodes? There were things I did to try to work around this. For instance, I would take out a segment from the start node to the end node. But it was going to be very difficult to manipulate and to say, all right, well, if you can't go directly to the end and you add one more node in there, then you have to go back and take out that node's that given node's segment to the end, so that it doesn't go directly to the end as well. And so that was ultimately just going to end up being somewhat like a greedy algorithm, and it was going to become more complex than was really needed in this assignment. So rather than try to manipulate Dijkstra's and really end up with something that's not Dijkstra's, I chose not to use it. Also, if I put in just a starting node and I didn't tell it where to finish, it just calculated the shortest distance and paths from the starting node to all other nodes in the map. In other words, it would just go from 1 to 2, and then 1 to 3, and then 1 to 4. And it didn't route all of the nodes together like I had expected it to. So this just goes to show we need to look at our functions carefully before attempting to use them. Moving on, this code was already in here, and it centers the XY coordinates so that they can be converted to polar coordinates. We have the thetas and rhos. And this is generating our y's from the TSP-GA function over here. And the only changes I made here were getting rid of some of the plots. So that way when we ran this code 100 times, we didn't have 100 different figure boxes popping up. As we go along, we can see that it's constructing the Y matrix. And ultimately here, I took our XY coordinates produced by this greedy algorithm and put them into separate matrices just so that we could see them individually. So we have our X matrix here. This is the feature set, and this is what's going to be most critical for us. So we have our thetas and our rhos. This is where we get into a separate set of features. We have our sequence produced by the greedy algorithm and the corresponding X and Y features associated with that. Note that these are going to be sorted by Cartesian X. This theta is sorted by itself. And now it's finished running. So you can see it didn't take too long to run. It's only taken about 6 minutes, maybe 7 since I started running it before the video. Anyhow, this theta is sorted by itself, and the rho is associated with theta. So these Cartesian coordinates do not correspond to this theta and rho. However, they are sorted by ascending x. So the y may or may not help us, just like the rho may or may not help us. But as Professor Rich noted, the more features, the usually more accurate. We also have our y's, and I just added this little code at the end so that we could see when the code's done running. Since I suppressed all the different outputs here, the things that didn't have semicolons, I went ahead and suppressed them so we didn't have a very large command window. And since there aren't any plots to show us a conclusion, I just wanted a little bit of code so that I could make sure to know when the code was finished running. As a preview to the next video, this is the similar code that we'll be using. Here we have an XY matrix feature set, which has our features and the targets. In this case, this bit in parentheses right here is pulling out Y3, that third node, that third element in the sequence, to try to predict just one node, which is a lot easier, or at least I would think, than producing an entire sequence. Y1 is not a very good choice because it'll always be correct. We're just choosing to start at 1 by default. And then the y's will get progressively worse as we go on because y2 is usually pretty close to whatever y1 is. We've already chosen our start, and so the next node will probably be the same for each sequence. But once we get on to y3, y4, y5, the further out we get from our initial given starting node, our certainty, the less certain we'll be. So what we want to focus on is our regression learner, and Keith will talk about the Bayesian classification as well. But just to give you a little taste of what our feature set actually looks like, I want to show you our x's and y's. So along the columns, we have our separate features, and then the rows, of course, are just different records, so that we have a nice large test set here. 100 features, or 100 sets of features. We have actually in total 50 features, as you can see here. 50 columns, each one representing a distinct feature. So these first 10 here, first 11 I believe actually, are thetas, and then we also have our rows. And now here you can start to see the sequence produced by the greedy algorithm. And for the most part, you can see it starts with lower numbers. We have a lot of 1s, 2s, 3s, and 4s in these earlier nodes in the sequence, and then we start getting into larger numbers, 9, 7, 8, 6, 10, over in the latter half. Hopefully this will make it easier to predict. We also have our random sorted x's over here, the ones that correspond to these nodes in the sequence, and then besides those, the y's that correspond with their respective x's. So hopefully those features will help in producing accuracy. It would also be interesting to see how the sequence that was produced by the greedy algorithm compares to the y. So let's just take row 4, for instance. We have 1, 2, 4, 5, 6, and row 4, 1, 2, 4, 5, 7. So just in the first 5, it's almost 100% accurate. So then we have 3, 10, 7, 8, 9 in the actual row here for our 4th record. And then we have 6, 8, 9, 10, 3. So it got the nodes almost exactly right. Somewhat different order, but you can see that they're very similar in their outputs. So hopefully this will help improve our accuracy. Thus concludes the feature set examination, and I'll allow Keith to explain how we're going to use this and show how we can test with machine learning. Thanks for watching.
So for our code, we have here theta row sequence that was generated for it, x and y coordinates, all in our x underscore matrix. Our y underscore matrix is our targets, and putting them together will allow us to go into the regression learner. Up here, new session, select the XY matrix, which is the combination of them. And then, for example, if I wanted to figure out a prediction model for the second node, that's what I would click there. And then down here, I will want to select the data that I want to train with and to hold out. So for example, for this one, I'll just do first 3. These are the thetas. Then the first 3 rows, the first 3 of the sequences that were generated, first 3 of the x's, and first 3 of the y's. And then, of course, I will not select any of these, which are our target features. So I'll start the session. Go up here to linear, train it. As you can see, the root mean squared error is 1.4, and the blue here are the target node locations that the second one, or target node numbers, the second one has these numbers in them, and then these are the predicted values based on that. Here's the root mean squared error and the r squared. And then what I will do is I'll export the model. I'll call it as train model 2. Press OK. And I've already had it, but I'll overwrite it here, and now it's ready for prediction.